Welcome back. Let's finish by reviewing a lot of stuff we've seen all chapter. So where are we starting here? We're starting with making of a, what do you call this functional group right here that has a carbon that used to be a carbonyl. Yeah, there's a phenyl here. That's no change. Phenyl CH2, phenyl CH2, 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 alpha CH2. Carbonyl is now, it's got 2 bonds to S instead of 2 bonds to O. It's called a thioacetal. It's a geminal dithioether. You'll see other books and OWL reference it as a dithiane. Translation, 2 sulfurs on an alkane. Misleading name, but you know, if the sulfurs weren't there, that'd be a methyl. That's an alkene. Okay, what happens? We got 2 thiols. Do not let the fact that they're both in the same molecule throw you off. They will react independently as thiols. Acid catalyst, Dean Stark trap. This is good for all condensation reactions. And I want to remind you, this is a condensation reaction. The oxygen that used to be the carbonyl ends up there. And we'll do the mechanism underneath. There we go. I'm stretching it that way. Nice. First step, we're going to do red first, blue second, maybe a green third. I don't even know. We'll see. Remember, if you're going to use colors, you got to remind me. Okay. You got to activate the carbonyl so that it's more reactive towards a sulfur nucleophile. So that would generate an oxonium. The oxonium is very reactive towards attack by nucleophiles. And this would be a separate second step. And you will generate this intermediate here. Phenyl, CH2, carbonyl has an O that now has a new H. It also has a new sulfur that will be neutralized in a third step. Yeah, the sulfur that I drew here, I'm going to draw it for like a second. I'm going to have H plus right there. But the next step is to neutralize that. What are you going to neutralize it with? The conjugate base of your catalyst. And feel free to do this. Scribble out this H, show it up here. That will be the H that I erased down here. It used to be an H. This will be a new color that's not red or blue. It'll be understood to be the third reaction, even if you don't say it, right? And I need a little better arrow there. A lot of green here. Maybe my whiteout will be purple out. There you go. Crossed off the H, drew it here. Okay, then we're going to get a What do you call this? That'd be a good test question all by itself. What functional group is right here? It's not an acetal. An acetal has two ethers, in this case thioether here, thioether there. It's halfway to it. It's got the thioether here, and oh, somebody's going to, you guys are nice. I lost a carbon, didn't I? There's 3 carbons between the sulfurs. 1, let's see, 2, 3. That doesn't look very good. Bigger eraser. Oof, got rid of some sulfur there. 1, 2, 3. There. It's a hemiacetal with a sulfur instead of an oxygen. It's a hemithiooacetal. Acetal. I say it acetal, because if I say acetyl or acetal, then you start thinking about a CH3 attached to a carbonyl, and that's not the case here, is it? Once again, you will never be tested on pronunciation. Without further ado, we have to get from the hemithioacetal. And yeah, you guys are real nice today, not interrupting even though you're seeing mistakes. I lost an H off there, didn't I? Yeah, I needed to draw this and I didn't have the H. Okay. But I want to point out, if I let a mistake last and I'm about to move on to something else, that's when chiming in is a good thing. All right, clearly OH has to go away. I don't see an OH here. How do you make OHs into better leaving groups? We've done it many, many, many times. Protonation is one way to do it. And you generated sulfuric acid so you could use it again. And protonation would be step 1 in red. You have an oxonium which can be kicked off. Kicked off by what? Sulfur lone pair. Kick it off as a second step. Kicks off, and that's called water, isn't it? Where does the water go? Physically, where does the water go? It goes to the Dean-Stark trap and gets trapped underneath some toluene. You got water. And we have an activated thionyl. What? Activated thionyl? Double bond to sulfur with a plus charge is no different than an activated carbonyl. And this sulfur has CH2 3 times. 1, 2, 3. You don't have to draw them like this. But I do want to emphasize that sulfur in this conformation with the sigma bonds rotated around, it is ready to attack. It's right there. It's going to be intramolecular. It's going to be fast. And if I'm smart about things, I'm going to show the sigma bond between H and S, which needs to be removed in a second step. But the first step is much like step 1 here, created an activated carbonyl. What did you do after you activated the carbonyl? You attacked it with sulfur. And then what did you do after you attacked it with sulfur? Third step, remove the proton with the conjugate base of sulfuric acid. So let's have everything all set up here, 3 colors ready to go. We're going to have the base waiting for an opportunity to abstract a strong hydrogen, strong acids hydrogen. That opportunity does not yet exist. Once sulfur attacks, it creates a sulfonium downstairs, right here, there'll be 3 bonds to this sulfur. And the second step, it won't be a third step. Second step is to attack the sulfonium H, which has a pKa of less than 0, and generate your thioacetal. Oh, I already wrote it up there. I'm not going to do it again. So there you go. That's as short as you can ever make this mechanism. If you prefer doing the steps more stepwise, that is absolutely fine. Textbooks got versions of those, and our notes from previous days also have versions where it's broken down a little better for you. And in this last step here, we're using a strong base, because if you generate a thioacetal and the carbon that's the thioacetal carbon still has an H, that was one of our new pKa's, and we saw it was 30. And we can use that strong base, hydride in this case, to grab the H. We're going to be generating a nucleophile, a carbon nucleophile. That gets exciting. Carbon nucleophiles can attack things. Where am I going to put this? I think we're going to go light pink. Okay. And we're going down here. We don't need all that stuff at the top anymore. And what are we going to have? Phenyl, CH2, C, lone pair minus 2 sulfurs, 1, 2, 3. I got that. Nucleophile. It's going to attack a positive carbon in the second step. And what's the most positive carbon? This one right here in cyclopentanone, which I'll redraw down here because there's already enough stuff crossing each other. Cyclopentanone doesn't need activation this time to be attacked. We've got a super hot nucleophile. It will attack anything that even smells a little bit positive. And we can't combine this with the acid-base step in step 3 because it is a separate step. You must show me the results of 2 before you proceed to 3. And we lost a CH2 over here, didn't we? There's 2 CH2s. CH2, CH2, there. Phenyl, CH2-1, CH2-2, C, 2 sulfur still hanging around. New bond, very exciting. Carbon that got attacked is an O-. Carbon is also part of a cyclopentane ring. And that looks a lot like this. All that we need to do to get up there is to put a proton on the alcohol. How is that accomplished? That is step 3, using hydrochloric acid. Step 3. And you have this intermediate here. Oh, why do I say intermediate? It looks like a product. Well, later on, we're going to do stuff with it. So that was a good review of acetal formation. Acetal formation, in this case, thioacetal formation. Creating a dithiane that has a pKa of 30, so acid-base after that. Then the nucleophile generated by the acid-base reaction attacks the ketone. And then the intermediate here protonates with HCl. And we have that. I'm going to go grab something else from my other screen. See you in 2 seconds this time. Well, maybe not 2. I got to find my other screen. Get my snipperdoodle going here. And here it comes. I have my species there. This is the one before I put the, I'll just go back and show you. So instead of doing what I did here to make this, I copied this molecule. I can do other things with it. Take the H off with a strong base. It doesn't have to be H minus, just trying to show you that. Could be another really strong base. Potassium amide. Oh, I shouldn't do it this way. There's the blank. There's the blank version. And we'll do it down here. KNH2 is called potassium amide. You watch how you say it. If I said amide, which has the exact same spelling, what would be wrong with saying it like that? Well, amides look like this. Carbonyl nitrogen. So it's just pronunciation. Ide for amide, amide for this one. Once again, you don't have to pronounce them differently. I'm never going to grade you for pronunciation. I'm going to take the same H I took off before. And we're going to generate our thioacetal anion. CH2 once, twice, C minus, sulfurs here. 1, 2, 3. And in this case, we're not going to attack a ketone like we did in the previous one. We're going to attack whatever this crazy thing is. What is that? That's dimethyl sulfate. And it should be treated like this. Do you remember what X stood for in orgochemistry 1? X was an excellent leaving group. It usually was a halogen. In fact, the first 20, 30 times we saw it was a halogen. Why? Because a halogen as an anion is stable. Well, this is a sulfate ion, which is, as a leaving group, it's stable. So dimethyl sulfate is the cheap version of a methyl with an excellent leaving group. This is nothing but an SN2 reaction. Backside attack, methyl is unhindered. So this would be very fast. Chemists like to say it would be plus facile, to borrow from their French counterparts. Technical translation is very easy. So CH2 once, twice, down to a carbon that has 2 bonds to sulfur. 1, 2, 3. And it has a new methyl group. New methyl group. And then the next mechanism, which we'll, let's see how we do in here. We can definitely get through the next one before another break. What's happening in the next one? I didn't show the other product because I was scurrying trying to get it done during our break. The other product has to have sulfur in it, clearly. I don't see any sulfurs over here, do you? This is the dithiol that you started with on the previous page. What's the reaction that gets rid of a thioacetal called? And uses water to do so. Uses water to break down a thioacetal. Yes, you guessed it. It's called hydrolysis. And yes, you guessed it. You were responsible for the hydrolysis mechanism on your test. So let's do it. Clearly, you need to get an O onto this position. So somehow, some way, you need to activate that carbon towards attack. Sulfurs have to go. How do you make sulfur into a better leaving group? Translation, it's the same question as how do you make oxygen a better leaving group? Protonate it. We're going to use sulfuric acid. We're going to combine some stuff here. So just to be safe. Now on your test, if you wrote this on the first page of mechanisms, you're covered for the rest of the exam, okay? I'm not taking any chances with you. If I do it, it'll be on the page you're on right now. My methyl looks like it might be bonded to sulfuric acid there. Not true. You're going to protonate using a lone pair on sulfur. Next step, the other sulfur is going to kick that off. You made it into a good leaving group. What's the next step always going to be? Make it leave. Oh, you can't put it in red. Got to activate it before you make it leave. It's got to be blue. And now it's left. Let's write down what we have here. Phenyl, CH2 once, twice, down to a carbon with a double bond to sulfur. CH2 once, twice, 3 times SH. And don't forget, you generated a sulfur with 3 bonds. That's a sulfonium. You want to be real particular with its name. You can call it a sulfinium with a double bond. And now it is time to consider putting this oxygen on here, isn't it? Where's that going to come from? It appears that our only choice is water. Need a little room to the right. Put water down here. First step, you're going to attack. Carbonyl, sulfonium gets neutralized by way of resonance. You would generate an oxonium here. Oxonium is a strong acid. What do we do with our strong acids? Very often after generating them, we neutralize them. What base are we going to use? We're going to use our sulfate ion, generated in the previous step. Hydrogen sulfate ion. It's going to deprotonate. Second step. And not surprisingly, we're going to make a functional group we saw on the way to making the thioacetal. You see the same functional group on the way to breaking it, or hydrolysis. Sulfur, once, twice, 3 times other sulfur. And you have a carbon that's simultaneously a thioether and an alcohol. I think I'm going to redo that. Looking ahead, alcohol, show the bond. That is a hemethioacetal. I think earlier we showed how to get from that to the full acetal. How about going backwards from the hemethioacetal to the carbonyl? Sulfur has to leave. Sulfur is not going to leave until it's a good leaving group. How did you make sulfur into a good leaving group previously? Here it's leaving. It wasn't leaving until it was protonated and a sulfonium. Same story here. Protonated to make it a better leaving group, step one. What's going to make it leave? Well, oxygen has a lone pair. It can resonate in and kick it off. This time generating an oxonium. There's sulfur leaving with its H that you put on. I don't like that second arrow. First arrow, resonate in. Second arrow, lone pair on sulfur neutralizes it. And the last step is to have your carbonyl without an H. And keep in mind, you generated with the red arrows, this species here. And it can, with the third color, neutralize the carbonyl. Blue arrows made a carbonyl. Red arrows help the sulfur leave. And there you have it. And this is a pretty good spot for a break. We're going to continue with some more summary mechanisms for chapter 16. Oh, in case you didn't notice, we finished all the topics in chapter 16. We're just doing a quick little rundown review, early review. Wednesday will be review. Before I let you go in this segment, here's what I want you to do before Wednesday. I want you to find questions in tests. And unlike last semester, the one we don't talk about, Fall 20, you're going to be having a document that looks like old exams. You may even print this document. It won't be available to you until test time. You don't have to print it. You can do it off the screen. So you'll be copying some molecules down. I try not to, I'll make them a little smaller than real exams. And you'll be doing it by hand, all by hand, on loose leaf paper, which you will scan and submit to me. I'll be giving you a test protocol later this week. So these things we're doing here are very similar to the things you'll be doing on next Wednesday, test one. And I'm going to leave you with this for now, and we'll pick up with some more review mechanisms. And here we go, C in 5.